Welcome back. It's time for another lesson. This time we're going to be applying matrices to a different problem. And this time the problem is also not n equations and n unknowns, which I know I told you I wasn't really fond of that one. Although this one is more closely related to that problem than the last one dealing with optics. This problem is called the linear least squares problem. The idea is that you go in the laboratory, say, and you collect a bunch of data. Here is some data I happen to collect, not in the laboratory, but actually right on my laptop. I wrote a little program that went out and counted the number of files in a certain range of sizes and recorded the number and the size of the files. So I made bins of different size, and all the files whose size was in one bin, I counted those, and I took the logarithm of that count and graphed it as the vertical variable on this graph, and then I took the logarithm of the size of the file and graphed that as the horizontal. And you'll notice that there appears to be, quite surprisingly, or maybe not surprisingly if you think about it, but surprisingly, there appears to be a mathematical relationship between the number of files on my hard disk that have a certain size and the size of those files. And this kind of relationship is called a power law relationship. It is ubiquitous in nature and in society and in the universe. So, and we can talk about the reasons for that. In fact, in the project I refer you to a paper that describes numerous possible explanations for these things. But the fact is, whatever the explanation, these things happen a lot. And it's useful to be able to quantify how they happen and what exactly is happening. One way to do that is to try to fit the data to some kind of a model. And the model that we're going to use is that the logarithm of the count versus the logarithm of the variable we're interested in is linear. That's called a power law. If you go back and see what happens if you try to relate the actual count to the size, you'll see that the count depends goes like the size to some power, and the power is the slope of this graph. So the problem is I've got all this data, and I want to find what line most closely describes that linear relationship between these two logarithms. And so I want you to imagine that we have some data points, and we have this possible line that might be the right line, and I want to calculate some number which characterizes the degree to which this line is a good line that does fit the data pretty well. And so the notion is I compute this thing called chi-squared. I measure the difference between each of the data points that I found and this potential line that I'm about to find, and I add the squares of the differences between the line and the data divided by the uncertainty in my knowledge of the data. And the reason I divide by the uncertainty is that for those data points that have a lot of uncertainty, I don't want those to highly influence my choice of line. But the ones that have very little uncertainty, I want to make sure the line goes as close to those ones as possible. So I'm scaling the distance between the data point and the line by the uncertainty in that particular data point. The other reason I'm doing it this way is because underlying this calculation of the thing here, which is called chi-squared, by the way, is the notion that this data is normally distributed about the model. In other words, we imagine that in the universe there is actually a correct model, but that there are confounding circumstances dealing with the nature of randomness, the nature of my measurement, the nature of nature, whatever. There are reasons why these data are not exact but are distributed about the model. And the distribution we're going to assume is basically a Gaussian, a sort of a normal distribution. There are reasons to assume that as well, but I don't want to get into all that. There's this thing called, what is it called? The central limit theorem, which basically says if you take a bunch of random influences and add them together, the result ends up being a normal distribution. But that's a different lecture, a different set of slides. Let's just say we're going to calculate this statistic called chi-squared, and it's going to give us a measure of the degree to which the current line is a good representation of the data. And in fact, you can see that if the line were bad, we'd have a larger chi-squared. If the line is good, we'd have a small chi-squared. So we're basically looking for so the idea is I can calculate chi-squared if I'm given a line. So the notion is if I try a bunch of different lines, then the one that gives me the minimum chi-squared is the one I want. So that's why it's called the least squares problem, linear least squares, because I'm looking for the least of the sum of the square deviations from the model. Okay, now, so let's look at our model. Our model is some kind of a superposition of a bunch of different functions, and each function is weighed in with a parameter. I call the parameters here A, B, and C, and I call the functions f1, f2, and f3. For our linear model, the idea is that f1 is just going to be x, and f2 is just going to be 1. Let's look at that. So we have data, y data and x data. This is actually from my data set. So those numbers are the logs of the counts, and the x's are the logs of the file size. So the model is going to be a times the log of the file size plus b is equal to the log of the count. That's the idea. And so my model, if my data are vectors, vertical column vectors, my model is a vertical column vector that corresponds to a number that I compute by multiplying the x by a and adding b. So you can see now that f1 is just x, and f2 is just 1, and c is going to be 0. There is no f3. I'm just using two functions in this example because I'm fitting to a two-parameter superposition of functions, which is, in this case, happens to be a straight line. What I want to point out is that I can rewrite my model as the product of two matrices. The first matrix is a 2 by m, so m is the number of data points, and n is the number of parameters. So it's a 2 by m. I should say it's an n by m. It's the number of parameters by the number of data points. So it's an n by m matrix. And it basically just represents the functions. So the first column is f1 of x, and the second column is f2 of x. And if I multiply that n by m matrix by my parameter vector, which is an n by 1, I end up with an m by 1. You know, the rules are that if you multiply two matrices together, if you've got an a by b times a b by c, you get an a by c. In other words, the middle dimension, the number of columns of the first matrix and the number of rows of the second matrix have to match. When you multiply them together, each element in the new matrix has a b element sum that goes away. The b dimensions go away. And so in this case, if you have a 2 by m multiplied, I didn't say that right, it's an m by 2. Yes, an m by 2 multiplied by a 2 by 1, you get you end up with an m by 1, which is what we want. Okay, so the point is, of course, that the function 1 is x, function 2 is 1. That's what I was trying to get at. And so we can rewrite the model as a product of a matrix. The matrix just involves the functions that we're going to use and the x part of the data, the x data points. And alpha is going to be my vector of parameters. It's just a list of the parameters of the model, the linear coefficients that I'm using to superpose the functions. That's the idea. So let's think about the fact that y star is m times alpha, and let's see if we can figure out how to compute chi-squared as a matrix operation of some kind. So first of all, I need to introduce a new matrix. In addition to this model matrix, the M matrix, I have a matrix that keeps track of the uncertainties. So the S matrix is just a diagonal matrix that has 1 over sigma squared for each of the data points. And notice that sigma is not a constant, but each data point can be different. Okay? So then I can rewrite chi-squared as y minus y star transpose times S times y minus y star. Now, y minus y star transpose, of course, y minus y star is an m by 1. Y minus y star transpose is just the transpose of that, so it's a 1 by m. It's just the column vector turned on its side. And and S is square, so it's an m by m. So if I multiply an m by m by an m by 1, I get an m by 1. So S multiplied by y minus y star is a column vector. And the interesting thing is a row vector times a column vector of the same dimension is also called a dot product. And it's simply the sum of the corresponding elements multiplied together. So I just multiply each of the elements of y minus y star by its own self, and and I add them. So it's the sum of the squares. It's exactly the numerator of the chi-squared. Of course, divided by sigma squared because of the S matrix stuck in the middle there. And so you can see that that's the same thing as chi-squared. And if I put in the definition of y star, then I can write the whole thing as a compact matrix multiply with the parameters explicitly thrown in to the mix. So I've got chi-squared in terms of the x data, in terms of the sigmas, in terms of the y data, and most importantly in terms of this vector of unknown parameters. So there we have chi-squared, and the question is, how do I figure out what parameters minimize chi-squared? Well, as most calculus students will tell you, if you want to minimize something, you have to take the derivative with respect to the variable the variable you want to vary in order to minimize. So if we take the derivative of chi-squared with respect to the alpha sub I parameter, the ith parameter, what we get is basically a derivative in a certain direction in parameter space. And what I want to point out is that if you take the derivative with respect to each of the parameters and set those equal to 0, that's sort of like taking a gradient in parameter space. If you've had Cal 3, then you know what that means. If you haven't, let me just appeal to your intuition. If I take the derivative of that expression above, the chi-squared guy, with respect to alpha, it's going to be a product rule. The thing on the left and the thing on the right have to have their derivative taken independently. If I just focus on the thing on the left and I take the derivative with respect to alpha, notice the y doesn't have any alpha dependence. The m part is linearly dependent on alpha, so that means I'm just going to end up with an m transpose. And that's it. That's the only thing that's going to happen. Of course, when I do the same thing for the term on the right, as I apply, say, the product rule, I'm going to end up with an m on the right, but the y minus m alpha transpose on the left will be the same. And if you look at those two sides, you'll see they're transposes of one another. So I can set either one of them equal to 0, and I'll have the thing set up correctly. So the idea is I just worry about one side, and that's m transpose on S multiplied by y minus m alpha. That has to be 0. If that's 0, its transpose will be 0, and the whole thing will be 0. So the details of exactly how we get there aren't as important as the fact that we can write chi-squared in terms of matrices. We can take the derivative with respect to alpha, and then we can solve. So if I multiply that out, you can see that the requirement that the thing be 0 is the same as saying that m transpose times S times y has to be equal to m transpose times S times m times alpha. Well, I can think of those matrices multiplying, see, alpha is the unknown, so I can think of those matrices multiplying alpha as a chunk, as a single matrix, which I can multiply on both sides with the inverse, and I'll get alpha. So the thing that matters is I can construct this M matrix if I know the model. I can construct the S matrix if I know the sigmas, and I can construct this whole monstrosity and apply it to the y vector, the data vector, and compute immediately the parameters. And I can do it in a general way that can involve as many functions as I like, and it's fairly straightforward. So let's take that idea and let's look at the actual code that I posted to ACE so you can see how it's done. Okay, so here's the notebook I posted on ACE. I'm not going to go through every single cell, but I want to go through the main points so you guys have a sense of what it's about. So first of all, there's a little note about power law distributions, which I've already talked about, and there's a paper here that you should go read, or you don't have to read the whole paper, it's quite long, but there are good examples in there of natural power law distributions that occur, and we'll come back to why that's interesting later, but I just wanted to point out that this link is there and that you should follow it and at least read the sections of the paper that give examples of power law distributions. So the next part is the little bit of code I use to go out and track down the file sizes in a directory on my computer. And you can see how it works. I pass in the directory, and I pass in the minimum and maximum sizes I'm interested in, and it gives me back an array of sizes. Now, you should edit this to match your system, or if you like, you can just load the data that I put on ACE from my system by executing this cell. You wouldn't even need then to execute this cell at all. So this little bit of code here, basically, if this is a 1, you edit this to make this a 1, then it'll execute this branch of the if, and if it's a 0, it'll execute this branch of the if. You can look at this and see what it's doing. In the case of the top branch, it's opening a file for writing. Open mydata.csv for writing. It creates a CSV writer object, and it writes all the rows of the file using the data that's in the array sizes. And then it closes the file. That's how I created the data file that I posted to ACE. If this branch executes, it goes out and opens the file, it creates a CSV reader, it loads the data up into the sizes array, and then closes the file. So basically, the top branch creates the file, the bottom branch reads the file, and loads the data from the file into the sizes array. So that's the idea. And let's actually, what I probably should do is go ahead and comment this one out. And I'll post this modified version to ACE so it doesn't go out on your computer and try to look in the user Steve desktop folder, which probably won't exist on your computer. So so there you have it. Okay. Now, what happens when you make a histogram of the log of the sizes of this thing? You'll see that you get what looks to be an exponential kind of distribution. It turns out it's not exponential. It's actually a power law. And so the question is, how can I tell the difference between an exponential and a power law? And the answer is, I have to graph it. In this case, what I do is graph the log of the count versus the log of the size. And one thing I want to point out is when I go to do the logarithms, I'm taking the log of the count plus a little more than 1, and the reason I do that is because when you get down into the basement here, when the count gets small, if you happen to get a count of 0, it turns out to be bad, because you take the logarithm of 0 and the computer complains mightily and the thing comes to a crashing halt. So I want to add a little bit to the log of the count in order to avoid that. It's only really relevant at the low end, and so that's the only. But here at the low end, we have low reliability. That the counts are small, and we have a lot of statistical fluctuation. Remember from our earlier experience with Poisson distributions that whenever you're counting something, the counts are distributed in a Poisson distribution, and the uncertainty in a Poisson distribution is like the square root of the count. So when you're counting big numbers like 1,000,000, the uncertainty is plus or minus 1,000. If you're counting small numbers like 10, the uncertainty is more like plus or minus 3. So it's a 30% error with a small count like 10. It's a 0.1% error with a big count like 1,000,000. So that gives you an idea. So then here's some prose in the notebook on ACE that goes through the same math that I described in the slide. So I'm not going to go through all that again. The punchline is the same. The parameters are the inverse of this model matrix thing with the S matrix built in, and then the data is on the right, and the whole thing is exactly the same as what was in the slide, so I'm not going to do that again. And here's a Python function that does exactly that. First, you pass in the uncertainties. It calculates the S matrix as 1 over the uncertainty. It's a diagonal with 1 over the sigma squared. Then the M array, you pass in a list of functions already having been applied to the X data, and we make an array of those functions, and then we take the transpose to get these vertical columns that correspond to each of the functions applied to the X data. Then we compute M transpose dotted into S dotted into M. That's the MTM matrix. We take its inverse, we get MTM inverse. Then we multiply M transpose by S by Y. That gives us, that's this part right here, okay? And then we multiply the whole thing together to get alpha. So the whole business of doing the fit is just a few lines of code here. You can see it's quite easy. Then we calculate Y star, that's just M times alpha. And then the function returns the parameters alpha, the computed value of the model, that's Y star. And I went ahead and sent back MTM inverse because it's sometimes called the covariance matrix, and it can be useful in estimating the uncertainty in the parameters. So here we get our function 1. It's just a 1 everywhere. Function 2 is just the X values, and we calculate sigma as 1 over the square root of the Y values. Now it's 1 over the square root because we're taking the log of the counts. And so if you think about the error in the log, it goes like the error in the count divided by the count, because d log x is dx over x. And so if the error in the count goes like the square root of the count divided by the count is 1 over the square root of the count. So the sigma goes like 1 over the square root of the count, because we're taking the log of the count. So we call the do-fit function, we pass in the two functions, we pass in the X data, we pass in the Y data, we pass in sigma, and out comes the parameters, the model, and this thing called the covariance matrix. We're going to pull out the slope and the intercept of this line as the parameter sub 1, parameter sub 2. Those correspond to the coefficient of the first function and the coefficient of the second function in the superposition. And then we're going to plot the error bars associated with our data and the model. And you can see that we get a lovely straight line model right through our data. Very nice. So that's all there is to that, except I want to know how well do I know the model parameters. So there's a bunch of different ways to do this. One is to look at the diagonal elements of the covariance matrix, which is an interesting approach. Unfortunately, it's difficult to explain, so I'm not going to actually even try that. But there is a much more straightforward brute force approach that I happen to like a lot, which I want to share with you. So the notion is this. We have a model that we believe explains our data well, but we want to see how well the parameters match the data. And so the idea is to use what we know so far about the model to generate a bunch of additional data that's not real data, but that is statistically like the data we did collect. And then we reapply our fit technique to this statistically similar but fabricated data many times, and look at the variation of the fit parameters as we repeatedly fit this pseudo fabricated data. So let's see how that works. So basically I'm going to do 1,000 trials. I'm going to keep a list of the M's and the B's. In this case, it's a linear model. I'm going to calculate fabricated Monte Carlo data. I take the model and I add a normally distributed random value to each element of the model, multiplied by the uncertainty in that particular element. Remember, sigma is an array. The normal distribution gives me normally distributed random numbers between minus infinity and plus infinity with a standard deviation of 1. So this is going to give me a standard deviation of sigma, and I'm going to add that to the Y stars, and then I'm going to fit it. I do a fit of this Monte Carlo data. See, it's MCY I'm fitting. I get a Monte Carlo alpha. I throw into the M list the Monte Carlo alpha M value, and in the B list I throw in the Monte Carlo alpha B value. And now I have a list of slopes and intercepts from each of these 1,000 fits. I calculate the average slope, the average intercept, and then I come down here and compute the sigma, or the standard deviation of the slopes that I got, and the standard deviation of the intercepts that I got. And then I just print out the results. And to compare, I'm going to go ahead and print out the corresponding elements of the covariance matrix that are supposed to, at least in theory, be like those. And as you can see, my Monte Carlo slope was, my fit slope was negative 0.652. My Monte Carlo uncertainty was 0.04, roughly 0.039. And my intercept was 14.06. My Monte Carlo uncertainty, one standard deviation certainty, was 0.58. If you look at the covariance matrix results, they came out almost exactly the same. So my Monte Carlo approach appears to produce, in this example, results that are very similar to the covariance matrix. When you go to nonlinear fits or to more complicated fits, then the Monte Carlo actually can give you better answers because it automatically takes into account any interdependencies between the various coefficients. If I do a histogram of the slopes, you can see that I get a nice mean, negative 0.65, and there's a nice sort of almost normal looking kind of distribution about that. The other nice thing about these guys is I can easily extend this to look at confidence intervals. I can figure out how far out do I have to go in the slope to contain 95% of the values that I get here. And it's quite easy to go out and figure out what the uncertainty in the slope would be to have a 95% confidence that you have all the slopes that you could possibly have gotten. And the same way with the intercept. So the other thing I wanted to point out, we saw before when we did the Demon algorithm how to do a fit using the SciPy package curve fit. And I went ahead and repeated the same fitting procedure using that package. And I also repeated the Monte Carlo error estimation. And it's just comforting to know that we got basically the same answer using that package. So, and sometimes it's good to do things more than one way to give yourself some confidence that it's right. So that's it. The project this time is basically for you guys to read this paper or read the parts of it that talk about power laws. And what I'd like you to do is to find some other naturally occurring data set that exhibits a power law distribution. And I'd like you to fit that data and check the uncertainties in the parameters to make sure that they're reasonable. And you don't have to use an example from this paper. You can just think of something that you think might have a power law distribution and go and collect the data, figure out a way to collect the data, and then check it. So that's the idea. We'll see you guys next time.